Welcome to a course on complex analysis. In this lecture, we are going to talk about an important ideology which is required for doing the entire analysis hereafter. Yes, that is the concept of continuous function. As it played a major role in the real analysis, it is going to play a major role in complex analysis as well. Let us explore that in this lecture. So, let us start with the definition of a continuous function. Even though we studied the definition in real analysis, the same is to be followed in complex analysis as well. That is, a function f is continuous at a point z naught if all three of the following conditions are satisfied. So, what can that be? So, while studying real analysis, we have seen the epsilon delta definition of a continuous function, and with the help of a limit also we studied some definition, and in a theorem we proved the equivalence. Actually, equivalence is proved, and topological definition we have studied. All these things are there, and those definitions shall be applied to any metric space. Here, in complex analysis, we have restricted ourselves to only the Euclidean metric. So, based on that Euclidean metric only, we are talking the things. Here, coming back to this one, the first condition is limit z approaches z naught f of z. This limit must exist. Okay, and the second one is your function has to be defined at this point. So here, just by saying f of z naught exists, it means your function has to be defined at that point. And the final condition is your limit as z approaches z naught f of z must be same as that of your function evaluated at that point. Okay, so this is the definition of a continuous functions. Hope I don't need to explain much about it. In other words, now I am going to give you the epsilon delta definition of continuous function. F is continuous at z naught if for every epsilon positive there is a delta positive such that absolute of f of z minus f of z naught less than epsilon whenever absolute of z minus z naught less than delta. While talking about the definition of a limit, we have excluded 0. That is, the function may not be defined at the point z naught in order to define a limit at z naught. Whereas in order for a function to be continuous at a particular point, the function must be defined at that point. That is what we are trying to convey here. Okay, and here some note that we would like to make here is suppose these are the results that we have studied in real analysis itself. Suppose f and g are continuous at z naught, then your f plus g, f minus g, the product fg, f upon g. Only for f upon g, we have g of z naught is not 0 or continuous at z naught. These are some results and proofs that we have seen during the real analysis itself. So coming back here, this is a theorem. So I don't actually remember the theorem number. I suppose this is theorem 4 of our course. So theorem 4 that tells us that a composition of continuous functions is itself continuous. So hope you people remember that we have seen the proof in the course of real analysis itself. There we have proved in a general setup. Actually, between any metric spaces, x is considered to be some metric space and y is considered to be some metric space, and z was considered to be big is z was considered to be some other metric space. There is a mapping from f to y, and there is a mapping from y to z, and the composition is defined from x to z, and we proved the composition g composite f or f composite g. We write it either left to right or right to left. It is up to us. Okay, so we proved this one is continuous with the general metric setup. Here we are going to prove it for the complex setup. Okay, that is just we are just going to replace every metric with absolute metric. Okay, in the statement it is given that a composition of continuous functions is itself continuous. So let us take, let f and like what, f and big F are continuous functions on some domain. Okay, actually we shall consider this on some, okay, some domain itself we shall take. Okay, now what we are going to do is that in particular f of z is defined from some subset of complex numbers to complex numbers, and big F of z is defined from f of s. Okay, or yeah, f of s, which is again a subset of c to c. Okay, let us also write w is some f of z and big W is some big F of z. So this is how we just take things. Okay, since continuity is supposed at all points of the respective domain, whatever may be the domain of the function, at all the points of the domain the function is continuous. That is what we are trying to say. Here we are talking about the continuity at all points of a set. It means if a function is continuous at all points of a set, then we say the function is continuous in a domain, in a particular set. Okay, hope you people remember or recall these things from real analysis. On the respective domain, we take some z naught in S and talk the continuity at this point. Now function f is continuous at z naught, and hence by definition for every, okay, so instead of taking for every, we may choose some epsilon arbitrarily. So for given epsilon positive, there exists a eta positive such that, like, okay, I shall take eta positive, or if you want you can take delta positive, such that absolute of f of z minus f of z naught less than epsilon whenever absolute of z minus z naught less than delta. Okay, Now we'll have to talk about big F. Since big F is continuous at f of z naught. So why do we take f of z naught? So we'll have to look at the domain of the definition of big F of z. It is defined from f of big S. So this f of big S is the collection of elements w such that this w shall be written as f of z for all z like for z in S. That is, you substitute all possible points from S into the mapping and look at the images, put all those images in one set, and that set we call it as f of S. Okay, since z0 is a member of S, this forces you that f of z0 is a member of f of S. So at all the points of f of S, your big f of z is continuous, and the continuity is assumed on all points. That is why your big F is continuous at f of z naught. Okay, again, and hence now by definition we'll have to do something, right? So for given here we have used epsilon and delta. Epsilon and delta are some arbitrary quantities, right? That we know for sure. So here you will have to choose some okay, let me choose it as alpha. For some alpha positive, there is a beta positive such that absolute of big f of, at this point we are talking. So f of z naught minus, sorry. Actually, it can be any point f of z minus big f of z naught less than alpha whenever absolute of f of z minus f of z naught less than beta. Now, here you have epsilon. So, what we are actually going to do here, we are trying to connect these things, right? So, here you have S, here you have f of S, and here you have C. So, here you have your mapping F, here you have your mapping big F. Okay, this is going somewhere. Whatever, if you choose a point Z here, then this is mapped to f of Z here, and this is mapped to f of z. Now you will have to choose a point here. Based on this point, you must be able to identify. Actually, you have to choose a negligible quantity, some negligible quantity at this place. Correspondingly, you will have to identify some quantity over this part. Okay, over this part. And based on this quantity, you will have to identify some negligible quantity at this place. And this has to imply this condition, and of course, this will imply this condition. That is what we are going to do. So this is gonna happen. In general, these things are happening. Now let us mark this as equation 1 and equation 2. Now combining all these things, hence by 1 and 2, for given, okay, I am going to make use of different notations. Now I am not going to make use of epsilon, delta, alpha and beta for this case. For given any positive quantity, that positive quantity, let me denote it as lambda. There exists some, I'll have to identify some other negligible quantity, and let me choose that to be mu positive, such that absolute of what? So let us go the reverse way. Absolute of z minus z naught less than mu will imply absolute of f of z minus f of z naught is less than some positive quantity, and let me choose that positive quantity to be epsilon, and this is gonna imply absolute of big F of z minus big F of z naught is less than lambda. So here I have made use of epsilon, delta, lambda, alpha, beta. What are these things? Now let me resolve all these things. So I'll have to start with something. So this I'll have to make use of. So this mu is replaced with delta now. Actually, this is my delta. Okay, my delta implies my epsilon condition. Good. So my beta and epsilon are one and the same. Okay, and this del epsilon will imply alpha. So either I can have alpha or I can change this to lambda. Okay, this condition implies this condition and this condition will imply this condition. That is what we have established. So with which we complete this proof. Okay, so this is like, if you are not comfortable with this proof, you can make use of the proof that we have discussed in the course on real analysis. Just replace the metric dx dy dz with the absolute value. That's it. So now let us move to the next theorem of our course. So theorem 5, and this tells if a function f of z is continuous and non-zero at a particular point z naught, then your f of z is non-zero throughout some neighborhood of that point. So let us pay some attention and try to understand what is given in the statement. Given that the function is continuous at non-zero at some point z naught. Okay, given f is continuous and your f of z naught is not equal to 0. This is what given. Now we'll have to prove the function does not vanish at some neighborhood of the point z naught. So this is what we'll have to prove. Okay, so okay, by the continuity, what do we have for given epsilon positive? There is a delta positive such that absolute of f of z minus f of z naught less than epsilon whenever absolute of z minus z naught less than delta. So this is gonna happen. Now we can choose epsilon to be any arbitrary value, right? Since f of z naught is non-zero, choose your epsilon value to be absolute of f of z naught upon 2. Okay, for this epsilon we are choosing some delta, so that is happening. So what we have is absolute of f of z minus absolute of f of z naught is less than absolute of f of z naught upon 2 whenever, or let us simply say if absolute of z minus z naught is less than delta. So this is happening. Now in order to prove the function does not vanish, let us assume the contrary. Assume the contrary. That is, assume there is a point z in the neighborhood absolute of z minus z naught less than delta, at which f of z is 0. That means in some neighborhood with radius delta, we are able to identify some point z. At that point, function becomes 0. That means the function vanishes. This is the assumption that we make. Okay. So, and if you mark this as equation 1, then by equation 1, so what happens? Whenever this holds, so this is going to imply a function value is 0. So 0 minus absolute of f of z naught, and that is simply absolute of f of z naught, and this is less than absolute of f of z naught upon 2, which is a contradiction. So this cannot happen at all. Hence, in some neighborhood of z naught, f of z is not equal 0, and this is what we were intended to prove, and this completes the proof. Okay. Next, actually, I'm not going to prove this theorem. Let me just state this theorem and give you the hint to prove. The theorem states if a function f is continuous throughout a region R, that is both closed and bounded, there exists a non-negative real number m such that absolute of f of z is smaller than or equals m for all points z in R. So remember, this is some region R, not the set of real numbers. Okay, where equality holds for at least one such z. So this is what we'll have to prove. Okay, here we are given a function which is continuous throughout the region R. Okay, fine, well and good. So the function is continuous throughout a region R means in the region, at all points of the region, the function is being continuous. Okay, good. The region is given to be a closed and bounded region. So closed means it contains all its limit points inside it. Bounded means, so we are talking about the boundedness of some region in the complex plane. So if you like the region is given to be bounded means absolute of z is smaller than or equals some value. Okay, you may consider that may be any value for some alpha in the set of real numbers and for all z in the region R. So this is happening. So this is the boundedness meaning. Okay. Now what you have to prove is that the function, the image set is also bounded. Okay. Since f is given to be continuous throughout the region, there is no break or anything in it. We can write the function f of z as u plus iv, and this u is actually a function of x and y, and v is also a function of x and y. Now whatever may be the region that you consider, if this is your R and this may be your R, whatever may be your R, okay, so this is happening. If this is so, this means what? Absolute of this thing is gonna happen. Okay, and again you know that absolute of f of z is going to be under root u of xy squared plus v of xy squared Okay, because of the continuity, it is moving like something over this. Okay, we are not supposed to plot this actually. If you write f into f in this form, you just consider this as your x and this as your y, being consider x and y over this region. Okay, over some region over here in the xy plane, you can find out something, and this kind of a thing you may get for your u. Similarly, you'll get something for v. Since R is closed and bounded, this forces that your u as well as v has to be bounded. That we have seen in the course of real analysis as well. Because of the boundedness of u and v, this is bounded by some real number m. Okay, actually you can collect this one, and you take m to be the supremum of absolute of f of z for all like over z in R. Then absolute of f of z is smaller than or equals m for all z in R. So actually this is the ideology that I have given you. So meanwhile I have said something that your function shall be written in this way, and how to check the boundedness of a complex valued function. These things also we have discussed in this lecture. In the upcoming lecture, we are going to talk about the derivatives of the function, and after derivatives, we will work out some problems based on the concepts that we have seen till now, and then we will enter into Cauchy-Riemann equations. Till then, thank you.